Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, well, I'm really happy to have David Van Horn visit us today from Northeastern. David's been doing some great work on adding contracts to Racket and verifying the behavior of these contracts, and he's going to tell us about some of this today.
Great, thanks. Thanks for having me. I will say, so that there are many reasons why it's nice to be here, but one of them is that my mother has a software company in Texas, and she does records management work. So she's been she's been doing SQL Server work and stuff like that for like 20 years. And if I tell her I'm going to give a PLDI talk, she's like, "Oh, that's nice." But then when I said I'm going to Microsoft, she took a step back and thought I was somebody special. So thanks for that. Okay, so I'm going to talk about this work on trying to verify behavioral software contracts. It's joint work with Sam Tobin-Hochstadt at Northeastern. Yeah, I think so. Yeah, this is why you should not be friends with your colleagues on Facebook. Anyway, so I'm just back from this DARPA PI meeting in San Diego, and the project that we're working on has this thesis statement, which is that language mechanisms that capture design knowledge can be leveraged to qualitatively improve reasoning about programs. And I think that that's a thesis that's really been supported by the work here and with the RISE group. And so I'm really happy to be here talking about this because I think we have sort of similar goals. I'm going to talk about this thesis in the context of a particular language mechanism, which is contracts, and a particular sort of automated reasoning, which is verification. So contracts give you a way of writing down specifications as part of your program in the programming language that you're programming in, and I want to be able to verify those things. Okay, so the goal here is to have some sort of automated modular verification of higher order programs with contracts. And right, I know that there's been a lot of successful work here on verification of programs with contracts of a slightly different sort. So I'm hoping I can tell you a little bit about the sort of higher order bit here. Okay. So I want to start by telling this story in a simplified setting where I'm not going to talk about contracts, but I'm going to talk about types. Okay, and then we'll ramp it up to contracts. And I know Francesco's seen a lot of this talk at Uppsala, so I've tried to add some more details so that at least he gets something out of it. What's that?
Well, Romans used to say repetita iument, repeated helps to understand more,
yeah.
So don't worry.
Okay, so I'm going to try to get across the essential ideas here using this simplified model of Plotkin's PCF language. And I'll talk about PCF not because I actually care about PCF, but just because I can boil everything down to its essence here. Okay, so let me just give you some examples so you get your footing with this language. So here is a program up at the top, and I've just illustrated the steps that it takes to compute an answer. So this is integer division, 10 over this conditional expression. So we're branching on whether 7 is 0 or not. Of course, it's not, so we're going to pick 3 here, and we get 10 over 3, which is 3. Okay? Okay, so the point here is that we've got some basic operations, conditionals. Let's look at another example. So here, you'll notice that the thing that ends up in the denominator position is 0. And so the point here is that we've got errors in our language as well. So you can divide by 0 and get an error here. All right. We also have functions in this language. So here's the 10 over x function, and it's being applied to what's eventually going to be 3. So we plug this in for x and get 10 over 3 again and back to 3. All right, and not only do we have functions over numbers, but we also have functions over functions. So here is the apply to 3 function. It's taking in as its argument the 10 over x function, and so we eventually get down to 3 here. All right. Okay, so the way that I'm going to approach this verification problem is by doing a sort of symbolic execution. And the way that I'm going to do it is by extending PCF to do symbolic execution. So I'm going to call this language symbolic PCF, or abbreviate it as the symbol PCF. Okay, so here's the idea with this program, this symbolic PCF language. So I want to be able to take a PCF program and rip open and pull out a piece of it. Okay, so here's the apply to 3 function. And I want to be able to abstract it to some symbolic thing. And so while I'm telling you this simplified story with types, the thing that I'm going to abstract it to are types. Okay, so this is a symbolic value in this language. It's really it's sort of a black hole. So it's an unknown value, but what we do know is this specification, which is its type. Okay, so it's a thing that takes a natural to natural function, and it's going to produce a natural. Okay, and I want to be able to plug that back in to my PCF program, seal it up, and now I have a symbolic PCF program, and I want to be able to run that. Okay, and as I'm thinking about the design of the semantics, I'm going to have this design principle in mind, which is sort of what are the sets of programs that we're talking about in this symbolic one? Okay, so if we think about that symbolic thing, what I'm really talking about is all possible concretizations of this. So I could have picked any value that could be abstracted to that and plug it in, and now I'm back to just a regular old PCF program, and I want to be able to run that. And I want the semantics to be sound in the following sense, that all of the concretizations are approximated by my symbolic PCF semantics. Okay? All right, so let's look at some examples here. So this is just the example we saw before, and now let's start abstracting parts of it. So what if I abstract the numerator here? So I'm doing some number over 3 here. All right, so you just stare at this for a minute and you figure out, well, it's some number over 3, that's just some natural number. Right? So the rule here is that we extend our interpretation of primitive operations to say that some symbolic natural number over some number that's not 0, that just gives you back a symbolic natural number. Okay.
So about your notation, so you're writing this, your transitions as relations, and your delta is the transition relation.
Yeah, exactly.
And that's, you've added an element to the delta transition.
Right. So we're just doing reduction semantics, and this is our relation for interpreting these things, and I've written the relation that relates these two things here. Okay? All right, so here I've abstracted in a different place, namely the thing that we branch on here. Okay, so I'm doing 10 over, well, if this is 0, 2, and otherwise 3, but of course this represents all possible natural numbers, so it could either be 0 or not 0. All right, but that's easy to model as well. You just take both, right? You come to a fork in the road and you take it. So here we get 10 over 2 and 5 on one branch, and 10 over 3, 3 on the other branch. Okay, so the relation here is straightforward, right? If you're branching on a symbolic natural number, you take both branches. Okay. Okay, here's another example where I've abstracted the thing that ends up in the...
So the variation of the guard cannot raise an error, they are side effects free?
Yeah, so this language, so the language does have side effects in that there are errors. But okay, so let's think of, so this could be abstracting an expression that causes an error.
Okay.
And so the way that I think about it is, if this is some expression that causes an error, that's really that expression's fault, right? It's not this larger it's not the program I know about that's at fault for that error. So I'm only going to be concerned with errors that blame the thing I know about. I can make that a little more precise later.
Okay.
But errors are really the important thing that we're going to be concerned about in these examples. Okay, so.
Just to understand the concrete semantics.
Yeah. So one way to think about it is that these abstract values, and so the value, there's no error for values of type nat.
Okay.
Only computations. Okay. If this doesn't get cleared up, let me know because it's important. Yeah. Okay, so this is the thing that ends up in the denominator position, and so now we're doing 10 over some natural number, and so of course we could get a divide by zero error, or we could get some natural number here. Okay, and so the point here is that there is an error that's really the fault of this program, right? And I don't care about the errors of the things I don't know about. I care about the errors of the program I know about, and there is one here. Okay, but the relation's simple, so some number over a symbolic natural number, you either get some natural number or a divide by zero error here. Okay, so here's really the sort of first interesting example, right, which is that we've abstracted a function here. Okay, so I'm applying a function that takes naturals and produces naturals, and I'm giving it the number 7. Okay, so I don't know what this function does, but I know that if it's given a natural number, it produces a natural number, so it's sort of obvious what this should reduce to, which is just a natural number, right? It should just reduce to the range of this function here. So the relation here is similarly straightforward, where if we're applying a symbolic function that takes some inputs and it's applied to some values here, some arguments, well then we just get back a symbolic result that is corresponds to the range of the function. Okay, and here you should think of, thinking about errors, right? It could be that this function causes an error when given 7, but that would be that function's fault. Okay, it's not 7's fault. And I'll talk more about fault and who's to blame later.
So you also have non-termination as an effect?
So we don't really consider non-termination. So if this program doesn't terminate, that's fine. I mean, we're going to give an answer that corresponds to what happens if it did terminate.
Just to
Yeah.
clarify.
Yeah.
So suppose this function has a precondition. You have precondition your language.
So
when the precondition is violated, the fault is of the caller, not.
Yeah. So
how?
So in this simplified setting, there's no preconditions.
Oh, okay.
But we'll get there.
I suppose you have preconditions in just the typing.
In the type, right? So, but all of
Expressions are well formed, so they don't.
yeah, exactly.
typing.
So we assume everything is typed, and so all of those. So if I had applied this to the string Fred,
Assuming there's no errors.
right?
Because
Yeah, yeah. So the only error that we have right now is divide by 0, and we're going to scale that up later. Okay. Okay, so I can write down this semantics. This is in the Redux language that comes with Racket. So we've got this little domain-specific language for writing down reduction semantics. And there's a problem. So it's nice. It fits on a slide. Of course, the problem here is that it's unsound. Okay. So let me show you how it's unsound. So here's another example where the thing that I've abstracted is a higher order function. Okay, and this is really the problematic case because the rule that I showed you earlier just says that if I apply a symbolic function to some input, then what I get back is a symbolic value corresponding to the range here. So this is what it says I should get here. Okay, and right, that's fine. So if we think about how to concretize this, right, that's fine if we pick something like the apply to 3 function, but if we pick the apply to 0 function, things go wrong, right? Because here is just a straightforward PCF program where I've plugged in this thing for this unknown component up here. And what I get is going to be 10 over 0. And I get some error, and you'll notice that that's not represented up here. And also, who's to blame for this error is really the program that I knew about in the first place, right? Because I'm passing this 10 over x function off into some unknown context with the specification that it takes, that this function takes natural numbers and gives you back natural numbers, but there are natural numbers for which it causes an error, right? So it's really, this thing hasn't lived up to its specification here. All right, and the semantics didn't account for it.
You're saying now you're going to be forced into adding contracts to prevent this situation?
So first I'm going to revise the semantics to find this kind of error. And then yeah, if I have a contract language, then I can put preconditions on this sort of thing and avoid this error as well, right? So, so getting back to the thesis of that project, right? If we give programmers the ability to write down richer specifications, then we can do a better job reasoning about it. Because if types are our specification language here, we're just stuck with that this might divide by 0. Okay.
So maybe it's skipping ahead. At least the nice thing about types being your specification language is it's
you can just
more
check
easily
it.
decidable.
Yeah, right. Yeah.
And
so it's both. It's more difficult to reason about, but you can also do other more powerful kinds of reasoning. Okay. All right. So thinking about this example, what I really want to sort of focus on is what happens to this function as it goes off into this black hole here. Okay. So at this call site, this function is really being sucked into this black hole here. And what can happen now that we're in this sort of unknown land with this function? And really, so what can happen here is anything, so long as, we can do anything with this function so long as we play by the rules of the language. And for now, that means playing by the rules of the type system. So you could apply this function to 7, or you could apply it to 8 or 625. But if you apply it to 0, that's the problematic input that's going to give the error here. Okay, so it's obvious from looking at this function that 0 is the input that you sort of looking for to make this cause an error. But of course, in general, you want to consider all possible natural numbers here, all right? And it would take a while to iterate through all of them. But we have a way of applying this function to all of the natural numbers all at once, which is just apply it to the symbolic natural number. Okay? So in order to account for this stuff that happens in these unknown contexts, where the only thing that we're concerned about are what are the possible errors that could occur, we extend the semantics with this havoc relation. Okay, and the choice of names here is not accidental. This is sort of inspired by the havoc function from Boogie, which is all about sort of putting things in an arbitrary heap context, right, in a first-order language. And here we're talking about behavioral things, where it's all about putting these behavioral objects in an arbitrary context that can explore the behavior. Okay, so when you apply a symbolic function to some inputs, we just pick out the type corresponding to each input, and what havoc is going to do is basically do everything it can to this value at this type. Okay, and in particular, so at this type, the thing that you can do with this function is apply it to a symbolic natural number. Okay, so emerging from this, now that we've extended the semantics with this Havoc relationship. And so every time that you apply a symbolic function, there's sort of two paths. One is the good path, which is we just get the range, right? And which is sort of the no errors occur when this thing goes off to the unknown context. And the other path is let's try to find all of the errors in the nat to nat to nat context. Okay, and it finds the divide by zero because we applied it to an arbitrary natural number, and our semantics already says that 10 over some natural number is an error. Okay, so now we're back into a sound semantics, and it only got slightly larger. We had to add this. We added this rule here. Okay. All right. So we now have this soundness property that says all of the concretizations are approximated by the symbolic PCF semantics, and it's got this nice sort of verification condition it implies, which is that if you're error-free in the symbolic semantics, then for anything that you can plug in, you're error-free for the original PCF semantics. Okay? So in other words, you can verify the program that you know about, and you could plug something in that has an error in it, but it would be that component's fault. All right. Yeah.
Let's go.
Yeah, I didn't see how that was captured in the statement of verification, that if you do plug in some value,
Okay.
that you can have an error, but that the blame is on the thing that you plug in.
Yeah. So really, I need to talk about contracts to get the blame part nailed down in detail. I'm sure that the details of the blame and the typesetting could be worked out, but they're definitely worked out for the contract stuff.
Can you go back?
Yeah, sure.
So it's the soundness statement. So you're saying all the concretization. So you have a concretization. I was expecting. So you're saying all the concretization approximated by PCF, but this so it means that you are not missing any PCF program. You are not missing with what PCF. That's what you are saying.
Yeah.
Okay.
Yeah.
Okay. So that's.
So basically,
it's the other way around. Okay.
Yeah. If you started with a PCF program and pulled out parts of it and ran it, you would have approximated the original one.
Essentially, yes, you have an alpha. Essentially, that's what we're saying now. Now my question is, do you have a gamma connection between the two, or do you have a best approximation for each PCF program? I don't think so, isn't it?
I don't know.
Approximated in different things. Okay, let me state the problem like this. Which is the order in your domains? How you order programs?
So I'll show you in a minute. Yeah, I'll show you some of the details. Yeah.
Well, some should be with respect to some order. So
Okay.
which is this?
Yeah. Okay. Yeah. So just hold on to that.
The concrete can be sets of PCF programs. Because essentially, say this quad PCF program is approximates all these sets.
Yeah, exactly.
And now here on the concrete, you can take just sets. You have the empty set and all the possible programs, and then you.
Yeah.
This is your essentially how you do your gamma. Now we are thinking how you do the alpha. What is the order in the abstract? Well, you said that one program approximates more, and does not seems that you have some. You should not have a lattice structure. I guess you should have some other order here, because now we start.
Well, I'll show you the order.
Okay.
Okay. All right. So now let me try to sort of redo this with a language with behavioral contracts in it. So we're going to look at contract PCF, which I'll call CPCF. And the language is extended in the following way. So to our set of terms, we've got two new forms. So one is a monitoring form, which says that we've got some contract here, and we're going to monitor this expression with that specification. And if this expression doesn't live up to its contract, then we blame. Okay? And in this simplified setting, I'm going to not tell you about how the blame is assigned, but I'll actually show that in this talk. So we'll get there, but for now, you sort of don't need to worry about it. Okay, and now the language of contracts it includes just arbitrary expressions which encode predicates. So we can write down a predicate and say that this expression must satisfy the predicate. And that's sort of the Eiffel style contract system. And then to extend this to higher order contracts, because there's no predicate that we can write down for a higher order thing and hope to be able to apply it and check it at runtime, we have a constructor for functions. Okay, so this is a function that takes inputs satisfying these contracts and produces some output satisfying this contract. Okay, so you build up contracts out, higher order contracts out of these predicates. Okay, so here's a simple example. I want to check that 7's positive. So the way that you do the check is you just apply the predicate. If the predicate holds, you get the value back. Otherwise, you get blame. Okay, so we get 7 here. If you check that 0 is positive, well, you're going to get blame here. Okay, and now the crucial thing is how you do the higher order monitoring higher order things. So here I've got some function where I've omitted the body here, and I want it to have the specification that it takes inputs that are prime and produces outputs that are even. Okay, and I can't just check that against this function at this point in the program, right? So the sort of Findler and Feliason insight here is that the thing that you do is you produce a new function. Okay, so you delay the checks and produce a new function that, when it's applied, is going to check that its input was prime. Then it's going to apply the original function that we had here, and after which it's going to check that the result is even. So you've got these higher order things that you need to enforce, and the way that you enforce them is that you drive them down to a lower level and delay them. Okay, so this is how contracts work in Racket, for example. Okay, and now I'm just going to sort of replay the same story with the symbolic semantics for the contract PCF language. And it's the same idea where I want to be able to rip out pieces of the program and abstract them, but not just to their type, but also to their type and some set of contracts. Okay.
That works out. That transformation you just said works out even for higher order functions?
Yep. Yep.
I guess because you just keep distributing it down until you get to the point where you're talking about something that's not higher order.
Right. Yeah. So when you've got a contract violation, I mean, when a contract fails, it's always sort of at first order, right? It's
You're back in
yeah.
non-higher order world.
Yeah. And then the real contribution of the Findler and Feliason work was, you know, how do you enforce these, which is the driving down, and also how do you account for who's to blame, because that gets more complicated.
Sure.
Yeah. Okay, so yeah, so here I've just attached some contract to this symbolic thing. So the symbolic values are sets of contracts, or a type and a set of contracts.
But I suppose this driving contracts down to the first order values, it works. It depends on your contract language, right? I mean, if you're trying to state equivalences between functions and so on, this doesn't work.
Yeah. So there's some question about, like, what does it mean to be correct with respect to some contract, because, like, let's say I have a program that I say takes even numbers and produces odd numbers, but I never call it, right? So it could be the function that always returns 4. And if I said it always produces a prime number, well, it never breaks because we never got there. So by delaying those checks, you can, right, you'll never get there if you don't actually force that thing to happen.
It's equivalent to runtime checking.
Yeah, I mean, it's a runtime checking mechanism.
That's by
Yeah.
encoding it in production semantics. It's always
Yeah.
getting it down to runtime checking.
Right.
It's equivalent, even
Yeah.
though you think of it as, you're thinking of it as static checking. It's not.
Yes.
Right. But I'm going, the property I'm going to sort of verify is the runtime part of it. So if I say that, if I verify that this thing satisfies this contract in my program, what I mean is that at runtime, it never produces something that's not
You
prime.
might not know that. As I'm saying, this is the next one. You're not going to know that unless you actually. You might not know that unless you actually run the program, because it might get delayed to the point where it never.
Yeah, but so that's true, but I think our approach to verifying these things is just to actually run them, but in this sort of symbolic semantics.
Which is the same static analysis. That's
Yeah.
the thing. It's just approximating is this concrete semantic feature of the PCF programs, all the possible ones. So you mentioned runs for all the possible instantiation listing.
Right.
And then he wants to prove this safety. You say, okay, if in the abstract, when I abstract my function with these symbolic values, so essentially it's plain abstract interpretation. If I can prove it, then by Saunders' result, I know there is no wrong program.
Yeah. If you can
among
prove it,
this
if
one.
you can prove
If
it,
you
then
can
you're fine.
prove it's okay.
The negative is.
It's as usual, so
Yeah,
it gets
yeah.
incompleteness somewhere, and so it should not.
Okay.
So I have probably a related question. So what about, can you express that the function is monotonic, for instance, or you want to as input a monotonic
So
function?
this was my point, actually,
Yeah,
not
yes.
the one that
That's-
Mike said. So my point is that if you are interested in checking safety properties, then you can do this by pushing the contracts down to the base level. But if you want to check properties, things like, I have a program that's lambda f, lambda g,
Yeah.
and my contract says I want f to be extensionally equivalent to g.
Yes.
Or I want f to be monotonic. Then these are not properties of a single execution of a program.
Right.
And then you can't just push the things down.
Yeah, so that's just something that the contract language is not going to let you express. Now you can express, so I've shown just a really simple contract language here, and I'll show some more of the bells and whistles of what are actually in the contract language. So you can express dependency. So you can say, I take f and g and x, and the result is that f of x is equal to g of x. And that will check it for any particular x that you give it, but not for all x. So you can express things like that. But yeah, you can't express properties that can't be enforced, other than running the program and checking those things. Yeah.
Right, in a way, you still have incompleteness that's mentioned because you're doing static analysis, so somehow there is some incompleteness somewhere, so there are things you cannot going to get.
Well, this incompleteness has come up way earlier than even the.
Yeah, so
atomic
there's
issues or
there's a kind of incompleteness just in the contract language, right? Forgetting about static analysis or anything, you can't write down the contract that expresses those sorts of things, like that the function's monotonic.
No, but Francesco was saying that it's incomplete even in the limitations of what your contract language is.
Yeah, of course, sure. Yeah. Okay, so here's a simple example, right, where I'm checking that some natural number is positive, okay? And so of course you can get blame, or it could be that it was positive, but there's an important thing going on here. So when we check this, this predicate against this symbolic thing, you'll notice that the way that it reduces is we check the predicate, we apply the predicate, but then in the case that it holds, we've added that predicate to the set of contracts that this symbolic value satisfies. Okay, so when you get down to the end here, if that predicate holds, we've learned something about the thing we were talking about here. Okay, so the symbolic values remember the contracts that they've satisfied. All right? And then that's going to be important sort of downstream, where you may check this again, and if you remember that this is a positive natural number, then of course you just get back a positive natural number, and there's no blame here. Right? Nothing goes wrong. Okay, so the contracts influence the computation. And that's also true here when we think about our primitive operations. So 10 over a positive natural number, we just extend this relation to say that if you're doing 10 over something that is positive, that you're just going to get back a natural number here, and not a possible divide by zero. So here I'm saying, yeah, so that's sort of a shortcoming of the relation that I wrote down here. I'm sure you could add that to the relation, I just didn't. Yeah.
So it's not a way of thinking that essentially you start having some abstract domain with your math and whatever, well, with types. Now you are refining your abstract domain by adding essentially those contracts.
Right.
And now, as a matter of fact, your static analysis gets more precise because now you know that, well, it's posed, so it cannot be zero.
Right.
And so you get more precise. So my question is, can you get it constructively by just thinking through the abstract domains, the one of types and the one with pose, other things. And now there are standard ways in abstract interpretation for creating a more precise domain. So this looks a lot as a reduced product, essentially.
Maybe I really don't know about that. Yeah.
But it just seems that
Yeah.
this is something you can build. Giving these basic blocks automatically, you can build this one. And so that's why you get this result, because essentially now you're getting a more precise analysis and more precise result.
Yeah.
You refine your abstract domain.
Yeah. Yeah, I suspect that might be the case, but I don't know. Yeah. Okay. And so here's that higher order example that we saw earlier, except the difference is that I've attached a contract to the 10 over x function, which says that it's got to be given a positive number. Okay. And now, okay, so the first thing that happens is that we drive down the contracts, and now this function goes off to this unknown context. And what happens here is, remember, Havok gets to do whatever it wants with that value, but it always has to play by the rules of the language, which in this case means that it's got to respect the contract. So it takes this function, which we know consumes positive numbers, and it's going to apply it to a positive natural number, in which case there's no error here, right? So the important thing is what's not on the slide, which is there's no error, and we always get a natural number. And so we can verify that the 10 over positive x function can't be blamed, all right? And that's the kind of thing that we want to verify in this work. All right, and we have the same soundness and verification property here. But now when we talk about error-free symbolic CPCF programs, right, we're not just talking about divide by zero errors. We're talking about blame, which is all about arbitrary properties that a programmer wrote down. Okay, so it's a much richer sense of being error-free here. Okay, whoops. So now let me show you a little bit more about the details. Okay, so here's our semantics for the symbolic PCF, and it's basically just the stuff that I've shown you before. We've got this delta operation for interpreting our primitives. So the way we do conditionals is we ask if the false predicate holds on the value, and if false is in there, we take this branch. Right, and the important thing is that this predicate on an arbitrary boolean gives you back both true and false, in which case you'll take both branches here. The delta is also used here, so this will include things like if you add 1 to some actual natural number, you get n plus 1, but if you add 1 to some unknown natural number, you just get back a natural number. So here's our function application with a symbolic function. One thing I should say is we really do have dependent function contracts here. So this is saying we've got a function that takes an input satisfying C1, and we produce something that satisfies C2 with x being replaced by the actual input here. So this is how you can express something like I take in some natural number and I give you back that number squared or something like that. So we can express that. And what this is saying is that we've got a set of contracts attached to this function, and what you get back is some unknown thing that is refined by the set of range contracts here with the input replacing the x.
So how do you express this in your concrete syntax? You had contracts that were either M or C arrow C arrow C. I didn't see any binders there.
Yeah, so I just didn't show that.
Okay, fine.
But yeah, so the real way that you would express it is the right-hand side of the arrow is a function.
Okay.
A function to contracts. Yeah. Yeah.
Recursion?
Uh,
Can you terminate? No, you're not. You should terminate.
yeah, it's you cannot terminate. Yeah. So we handle recursion.
Do you have a simple example where you don't terminate? Which is the easiest one? Or among the easiest one? A minimal.
I mean, let's see. So you could just write down. I mean, the simplest example is just.
Function calls itself.
So we have a recursive binding. So you can say let x be x. That's the simplest non-terminating program.
Can your contracts diverge or be impure or something?
So your contracts, your contracts can diverge. And then there's also the really interesting question of what happens when there's an error in your contract. For what I'm going to show you, that's sort of swept under the rug, but there's work on accounting for that and who's to blame when a contract itself fails. And all we have to do is take that semantics and write it down. So we can handle that straightforwardly. Okay, and what else to look at here? Okay, and then here's our havoc function. And so it's indexed by the type. And all we do for base types is just say that this doesn't produce anything. Okay, and but for function types, what we produce is a thing that takes in this value and then applies it to an unknown thing corresponding to its input type, and then we run havoc at the output type on the result of that. Okay, so that's our havoc construction here. Okay, let's look at how contracts are monitored, and this will give you some more details about how the blame stuff works. Okay, so monitor is the little monitor form that I had in the concrete syntax earlier, and it's got these labels on it. Okay, and we've got this way of sort of tracking the blame, and you'll see it when we check. So flat is a predicate here. So when we check a predicate, and if it fails, we're going to blame F, and the way to interpret this is that F broke the contract with G. And the H here is really about sort of the origin of where these things came from. It's not very important, but and really the important thing here is that as far as the blame calculus goes, is that when you are when you're monitoring a function, the positions swap. Okay, so it's contravariant for functions. Okay, so the who's to blame switches as you do a higher order monitor. Okay, what else to look at? Okay, so you'll notice here that I've got this judgment that says that V, the way to read this is that V, we can prove that V satisfies C. Okay, so we're really parameterized by some theorem prover here. And I should really say theorem prover in quotes, because so for the simple system, this is what our theorem prover consists of, is if a value remembers some set of contracts and the contract that you're trying to prove is in that set, then you say, yeah, it proved it. Okay? But this is, I think, a big opportunity for, so this is, we're trying to monitor some value with a contract, but if you can just prove it, then you can eliminate the monitor here. So the way that we eliminate it is by remembering that you've already satisfied it. But you could plug in a much more sophisticated theorem prover here, and everything would get better. Okay. Right, so here's the remembering. So we check a predicate and we remember the predicate that we were checking here. Okay. Right, and these other rules just have the side condition that you weren't able to prove it, so you actually have to enforce it. Okay, so here's the soundness, which says that if E refines E prime and E reduces to some answer, then there exists some other answer that A refines such that your abstraction gets there. Okay? So I have to tell you a little about this part. And so the basic things of this refinement judgment are just that a value of some type refines an unknown value at that type. Okay, so contracts can refine values, so you can sort of arbitrarily add contracts on the left here. And if you want to check some expression, so the monitors or the checks can refine expressions here and say that we can get some unknown thing that we know satisfies this because we're going to check it here. And there are a few more things, but not really important here. But that's sort of the basics of this ordering here. Okay? So now let me tell you about how we scale this up to a more realistic language. So symbolic racket. So racket's a Lisp dialect that's in development at Northeastern and other places. So we've got a rich language of contracts, and we've developed an interactive verification environment. So when I say a rich language, what I mean is that we've got a real module system. It's an untyped language, so which just makes the problem harder. We've got real data structures, lots of base types, lots of primitive operations. The contract language, well, we've got the blame that I sketched for you, the dependent functions. We've got data structure contracts. You can do conjunction and disjunction of contracts, and you can write recursive contracts. And I'll give you some of the details there. Okay, and the reason why we scaled this up is going back to the sort of thesis of this project is that this is a really rich specification language, and the idea is that we should be able to reason better about programs by having all of these things. So it was important for us to be able to really scale it up to a full contract language.
No negation.
What did we do for negation? So I think that we handle negation. I can't remember actually right now. I can't remember if there's anything hard about negation or not. I'd have to look.
Like there should be, but...
Yeah, I think it's easy enough that I thought it wasn't even worth putting on the slide, but I can't recall. So here's an example where we're defining a contract for a list of natural numbers. Okay, so it's a recursive contract which says that it's either empty, so it either satisfies the empty predicate, or it's a pair constructed out of the not predicate and a list, right? This is the recursive thing here. All right, and now we've got a module here that's providing two things, insert and nums. And you'll notice there's no definitions in this module. So this is how the symbolic things get introduced, because insert and nums are going to be treated symbolically. And insert is a function that takes a natural number and a sorted list, and it produces a sorted list. Okay, and nums is just some arbitrary list of natural numbers. Now, the module that we're interested in verifying is an insertion sort module. So it requires this stuff, which we don't have definitions for, so they get treated symbolically. It defines a fold, sort of the usual fold left higher order function here, which folds this function over a list and some base value. Okay, and then so the way that you write insertion sorts is you just fold insert over the list and the empty list as your base value. And we provide sort at this contract which says you give me a list and I'll give you back a sorted list. Okay, so we're not verifying, sort of full correctness of this thing, but because it could give you back any sorted list, but this is the kind of contract that you might think about writing down and then erase it because it's going to be too expensive to actually enforce at runtime. Okay, and so what we can do is we can just type this into our REPL and say sort this arbitrary list of numbers, and what you get back is a sorted list of numbers. And again, what's important is what's not on the slide, right? There's no cooter of empty errors. There's no applying something that's not a function, right? So there's no kind of runtime type errors, anything like that. And also we have this this added property here that we know that the list is sorted that we get back. Okay.
Can you parameterize your contracts by other contracts? So could I have written a polymorphic list contract?
So you would have to. So polymorphism is difficult to enforce at runtime, but there's been work.
Well, not necessarily parametric.
Yeah. So there's been work on. So I think one of the lessons here is that if you can write down a reduction semantics for the original language, we think that it's sort of straightforward to turn it into this symbolic kind of thing. So if you can write down, whatever kind of runtime enforcement mechanism you can write down.
So I could say define contract list C and take another contract as a parameter.
So in fact, in the actual Racket language, contracts are just values in the language. So you just write that as a function. And we can do that. And you could also write down things. This could be a dependent contract. Like one thing that you might want to add to this specification is that the result is always a permutation of the input, and you could write that down. Our tool is not going to be up to the task of verifying that part of the property. It'll just verify this part, and then you'd have to leave in the runtime mechanism for checking the permutation aspect of it.
Would your tool be able to tell you that it was able to verify this part of the specification and
so in some sense, because you can look at what are the possible contract failures, and so you should be able to see that it never fails with it being not a sorted list. It would only fail with the permutation part.
That's cool.
Okay. So this is out of this Uppsala paper, and there's some more details there if you're interested. I want to tell you a little bit about the verification environment. So we're able to verify programs like this. So this is a program that our first-year students write. It's the snake game. So this guy is running around on the screen and trying to collect this food, at which point it grows and it dies if it runs into any of the walls, and it dies if it runs into itself. Okay, so it's an interactive, event-driven game where we're registering callback functions here to this event loop. It's broken up into a bunch of modules. We've got some contracts on the things that each of these modules provide. Okay, and if you wanted to verify this program, the steps that you would go through is, okay, so we've got one module that's sort of providing all of the image primitives. And it's really just requiring this underlying library, image library, and wrapping them with contracts. Okay, so if you wanted to, and you'll notice that so we're writing this in Racket, and if you wanted to verify it, you would just change the language. So this is our verified by abstract reduction language. You comment out the require to the primitive library. So now this module exports a bunch of things but doesn't define them. So they're going to be treated symbolically. And then you run it. You run it and you notice that there are no errors. Okay, so we can verify these contracts, which are somewhat sophisticated, right? So a position is a posin structure with two non-negative integers in it, for example, and that a direction. So we've got these kind of ad hoc data definitions. Things like the snake is a non-empty list of positions, and so on. And we can verify all of these properties in this program. Right, and those were the only changes we had to make. All right.
So this source code you show us, it's written by some student, or you wrote it and you verified it?
It could have been written by some student.
How difficult it is to use for
Uh,
steps?
So the tool could, I mean, I think it needs some work before it was unleashed on users. In particular, we don't give great feedback so one thing that we do a really bad job of, like if you leave a paren off or something, a parenthesis off or something, you've got some syntax error, like you get this awful error message, okay? And Sam and I have gotten really good at interpreting what went wrong there. And so I would never, at this point, I wouldn't give this tool to students to write.
Okay, suppose that syntax is okay.
Yeah.
But you cannot prove something, so how do you report the messages? So how complex are?
I should have had an example, but they're similar to the sort thing where you just get at the bottom in this sort of interaction window here, you get a list of possible results,
Okay.
Which could include error results. So you run your thing, and if you get some errors at the bottom, it'll tell you. It looks a lot like a contract violation in the real Racket language. So it says.
It does not give you, for instance, the trace saying. I'm just curious to know how you propose feedback to the user. Or
Yeah. So we have a
because
we have
it
a
can get
couple.
very complicated. So to understand what's
Right.
going wrong and.
So let's see. So one thing. So the sort of immediate feedback is just the list of possible results are printed down here. Now another thing you can do is you can add a keyword up here that says you want to see the traces, and at which point it produces windows that look a lot like my first slides with those diagrams. And you can also do a different tool to get an algebraic stepper. So you can step through the thing and watch where it's splitting and so on. So we actually have some decent tool support for exploring the semantics here. Yeah.
Does that stepper come out of Redux?
Yeah. So we're leveraging, so all of those things we're really just leveraging the Redux toolkit for our language here. Yeah.
When you do the symbolic execution and explore all these different paths, are you guaranteed that it will terminate if the program terminates?
Yeah, so that's a good question. So no, because in particular, you could write down a program and not abstract anything and just run it. And of course, it may not terminate. So yeah, so that's a good question. I think I'm going to come to that. Let's see, Nicole, how much time do I have?
Should look to start wrapping up.
Okay.
We have the room till 12, but.
Okay, all right. So I think I'm going to skip over most of the formal details of the sort of richer language here. Yeah, I think you sort of get the essence of it from the examples. So let me just skip through this. Yeah, so this is really
In a
just.
sense, it depends. It's just three of us. I mean, it depends on you guys.
I'm okay if you want to continue. So I don't know.
You okay too?
Yeah.
I'm okay.
Yeah.
Okay, so then JK, we have the room till 12. Take your time.
Till 12? Okay.
Yeah, that's the one.
All right. So let me just try to give you the highlights here. So here's our scaled up language where a program is really a set of modules and some top level expression, and a module is just a name, a contract, and a value. This should also include that this is an unknown value. Looks like there's something missing here. When we've got so module references are sort of syntactically distinct, and they're labeled with where they occur. So this is a reference to some module definition F, and it occurs in some module or top level called L. Okay. We've got lists in our language. We've also got pair contracts, disjunction, conjunction, and recursive contracts. These things are not so simple to handle. So one thing that you'll get out of this part of the talk is, what are the semantics of these things? So here's the way that programs reduce is we've got some module context, which really just serves to resolve the module references in our program. Otherwise, we've just got just a step relation here. Okay, so here's our sort of the obvious reductions. Okay, so function application. Remember, we're in an untyped setting now, so you could apply something that's not a procedure, and you get blame. And here, it's a slightly weird blame label here, because what you're saying is that this expression broke the contract with the language in some sense, which is a runtime type error, right? Because it wasn't a procedure. We have really two judgments in this system. So one is this value. We can prove that this value always satisfies this contract, and we also have a refutes, which says that this value never satisfies this contract. And they're not just negations of each other, because you can have something that neither proves nor refutes. If it's some unknown value, for example, well, it could be that it satisfies a contract, or it could be that it doesn't.
Fourth case, so which is you never execute this contract. You never. So it was the case you were saying before. You're never going to evaluate this one because it's just a simple enriched code. In general.
So sorry, what was the question then?
Okay, so in general, so I think the statement you're doing here is that when I have a contract, I have some context and I'm trying to see which is the outcome.
Right.
And so you say, okay, either I prove it means for every execution, if you reach this point, then it proves it, because I think you are parameterized by non-termination.
Yeah. So these things are.
If I reach this point, it's true.
Yeah.
Then you have the one that says, if I reach this point, all the times I reach this point, it's false.
Mm-hmm.
Suppose that you discover that x is 0, and then you divide by x. So every single time it's false.
Yeah.
Then you say, I don't know.
Yeah.
And then there is a fourth case, which is I never reach this point.
But that's handled at another level. So these things are only used when we reach a point. So you sort of avoid making these judgments if you never reach them.
Okay, implicitly there is.
Okay. So it's either I know I satisfy it, I know I don't satisfy it, I don't know either, or I never get here.
Okay.
Yeah. Okay. And just to give you an example, I mean, this is how like the primitives are interpreted with respect to this theorem prover. So if we know some value proves that it's a cons, a pair, then the way we interpret the car, right, which is pulling out the left component of the pair, is we project out the left component. And you need this. You can't say that this is literally a pair, because it could be, for example, a symbolic. It could be a symbolic cons and things like that. So you need this sort of projection helper meta function here. But if I know it's a cons, I know I can project out of it. If I know it's not a cons, I know that it's just a blame. If I don't know either, so I write it with this question mark, then I project and I blame. Okay. Module references. So there's really three kinds of module references, right? And remember, this is F. This is a reference to F occurring in the module labeled here. So this is a self-reference. And notice that there's no check, right? So we're referring to F, and it's got some contract, but we don't check the contract, because you think of the contracts as being established between module boundaries. So if you've got a self-reference, you don't check the contract. That's just the way that the contract system works. This is a reference to F occurring in G. So we take the contract on it and we check it when you make that reference. And this is an external reference to something where there's no definition available. So we check it against this abstract thing here. Now here's how the contracts are checked. You really need to have this distinction between a flat contract and a higher order contract. So a flat contract is just a contract that, is like predicates are flat contracts. They're things that you can just check at the point that you want to monitor them. Okay, so if C is a flat contract, and for now, okay, so what's flat? So a predicate's flat, a pair of flat contracts is flat, a conjunction of flat contracts is flat, and so on. So if it's flat and we can prove it, then you just eliminate it and remember that you've satisfied it.
So David, I'm confused by the previous slide actually. So the one where you had this checking self-references.
Yeah, here.
And you were not going to do any check?
Yeah.
Is that the one?
Yeah,
okay.
yeah,
So
that's
why
it.
is that? Why is that sound? I mean, if I have a module that says I'm going to provide you with a positive integer, and the module is f, and the implementation is that it's just going to return f.f and return 0 instead.
Yeah. So what happens is that you can. I mean, the way to think about it is that internally to your own module, you don't have to. You can break your own contract, and that's fine. But as soon as somebody else uses your module, there's going to be a contract boundary established. At which point this isn't the case anymore, and it's going to be checked here.
And so you'll get blame at which point? So when G calls f and tries to use f's the supposedly positive integer that's actually 0.
Right.
And then you'll blame f?
Yeah. So yeah, that's right. So yeah, if f doesn't live up to its contract externally, then it's going to be blamed, and internally it can do whatever it would like. Right. So you could, for example, provide some function that says you have to give me the input 5, and then it recursively calls itself with arguments that aren't 5 all the time, and that's fine so long as externally you're always given 5, and likewise with the returns. And this is just a design choice that comes from the way that contracts work in this language. And you could make a different design choice if you wanted. And if you wanted to check that contracts held within a module, you would just change this rule.
Okay.
Yeah. But there's no way to sort of break the module level contracts. Okay, so this is when we can prove that we can eliminate it. This is when we know that it fails, so we blame. And this is when we don't know, so we have to enforce it. So what this FC function does is it compiles the contract into a predicate. So the way to think about a flat contract is it can be compiled into a predicate. Okay, and this is the compilation for it. Okay, so if it's a recursive contract, you just move inside. I don't know that there's much that's interesting here. So flat contracts are easy. So if you have a conjunction, you just compile it to a function that checks the first one and then checks the second one. Right? So this is just turning all of these things into predicates. If you've got a pair, you turn it into a function that asks if it's a cons, and if it is, then it applies the first contract to the car. Otherwise, and then it applies the second part of the contract to the coder. That's the easy part. Here, so the distinction between flat and higher order is that a higher order has to be, potentially partially delayed. Okay. So here is a dependent function contract checked against a value where that value is a procedure. So we just do the sort of ADA expansion here, the driving down the contracts, and we blame if it's not a procedure. Right, and this is all, we've sort of pushed all of the work into delta telling us whether this thing is a procedure or not. Now, you can also have, so a pair of contracts can be higher order if one of the components is higher order. So this is how to deal with sort of composite higher order contracts. So if you've got a pair, then you produce a new pair that monitors both components. And if you can prove that this thing is actually a pair, and blames if it can't, and so on. So conjunction of higher order contracts is sort of straightforward, where you monitor both contracts here. Disjunction is the more interesting one. So the disjunction of two higher order contracts, it's not clear what the semantics of that should be, and who's to blame when something goes wrong. Okay, and so what Racket and other languages with these higher order contracts do is they make a restriction where they basically say that you can make a disjunction of contracts, but only one of them gets to be higher order. So you can have a flat contract and a higher order contract, but they can't both be higher order, because there's no good answer for what to do in that case. So we make the assumption that the left side is the flat one and the right side is the higher order one. And so we just compile the flat one and then monitor the higher order one.
So taking C or D as being, suppose I had int arrow int or string arrow string, then why can't you decompose it by saying, I'm going to test int or string on my argument.
Yeah.
And depending on the one that succeeds, I'm going to remember what should be the check that's done on the outside when the function returns.
Yeah. Yeah, so what happens in that case? So I think that at that level, it's you can work it out. But then when these things get more higher order, it becomes more problematic. I'll have to dig up the details for this, because
just because you need a bit of state to figure out.
So that's one aspect of it. There's more to it. I'm just I can't recall the details right now. But again, this has nothing to do with sort of the symbolic stuff. This is all just about the design of this contract language, which are design decisions that we didn't make, right? We just wrote down the semantics of what Racket actually does. And it makes this restriction where you can't do a disjunction of higher order things. Okay. And here is our applying unknown functions, and it's similar to before, where we're just getting the range and havoc in the other place, but here we have a sort of more complicated havoc construction, which has to decompose pairs and apply functions, because both, now we have new kinds of behavioral values, right? You have functions, and also lists can contain behavior because they can contain functions. Okay. And then the way that you run a program is you have to first, so the important thing here is that you do this sequencing where the first thing you do is you take all of the modules and you put them in a havoc context. Because the module is providing something and it doesn't really know how it's going to be used, so we have to explore all of the behavior there. And this is just a ramped up statement of the soundness theorem for this language. But it's the same as before, basically. And then our corollary about, if you don't see blame, you know that you can, no matter what you plug in, that you can't blame the program you know about. So that's what this is really saying here. So if f is the name of a program that that's concrete, meaning we know its definition, if the program doesn't reduce to a blame of that module, then there's no way to plug something in so that f is blamed. Okay, so this is really being precise about who's at fault. And really, we're reasoning about the program that we know about and ignoring the programs we don't know about. Okay? All right, so this was the original goal, right? Was an automated modular verification of higher order programs with contracts. And I'll say that we've succeeded, but there's some caveats here, all right? So one is that there's lots of room for improvement. And I think the biggest room for improvement, and it's something that, I think you guys probably know a lot more than me about, is how to do this part of the puzzle, okay? So, maybe you could plug in Z3 here and get some interesting results. And it's all going to, as soon as you do something better, the whole thing just gets better. And there's a nice, I predict that there is a virtuous cycle that's going to occur when you start doing a better job about what theorem prover you plug in here, because we have really just a simple theorem prover that we wrote ourselves. And then the other question is, well, is it really automated? Because it's not decidable. And so if you think automated equals decidable, then you might think that we've sort of, we haven't really achieved that. Okay. So I was going to talk a little bit more about how to make it decidable. I'll just step through that real quick, and then we'll wrap up. So the way that we're going to do it relies on work I've done with Matt Might and more recently with Ian Johnson. And it was really the sort of genesis for this work was thinking about how do you do program analysis in a modular way where, the sort of classic approach is you write down some whole program analysis and then you pull your hair out thinking really hard about how to make it modular, and then you write it down. But Matt and I have this sort of turn the crank style approach to going from, say, a reduction semantics to a program analysis in a systematic way. And all of the stuff I've been showing you is just a reduction semantics. So we've sort of solved the modularity problem up here, and now we should be able to just turn the crank and get out a computable program analysis from it. And so typically this is applied to whole program semantics because after all, what else is there, right? And we've applied this to Racket in the past, and Android and JavaScript. There's a group at Harvard that's applying it to an intermediate language for Coq, and there's a group at Oxford that's applied it to Erlang. So so this stuff is fairly useful and easy to apply. But another nice thing is that we can take the semantics that I've been talking about and plug it into this pipeline, and what you get out is a sound and computable modular program analyzer. Okay, I was going to tell you some more of the details here, but I'm just going to skip this stuff. I think the big point here is that we're really just writing down interpreters, and you iterate them to a fixed point, and you get this, these big graphs and these state graphs and so on. But they're always finite. But for me, the big insight here is just, this is just an interpreter. And
so why you say they are always finite? You can go forever.
Yeah, I skipped a step. I skipped a step. So I've got this machine semantics, and it's set up in such a way that the only approximation that I'm going to do is say that the heap is finite. Okay, and what that does is that sort of collapses the whole state space down to a finite space.
And even if the heap is finite, you still have.
And then you have base values.
Plus. Sorry.
Yeah, and then you have to deal with the base values as well.
Okay.
So making the heap finite is enough to make your function space. All of the set of functions that you can represent is now finite, which is sort of the piece I'm most concerned about. And then you have to do you have to have some abstract domain for the base values, like natural numbers and strings and so on. Okay, so the components are, sorry, let me back up just a step. So you've got this machine, and it's parameterized by functions that do push and bind. So push is like a stack push, but it's being threaded through the heap here. So our stacks are always finite, and binding is doing variable bindings, and that's also threaded through the heap here. So that is also.
Sorry, I'm missing the intuition. So if you have suppose the Fibonacci function, how you abstract it from
So you
initial
have.
value or
So if you have the Fibonacci function,
Yes.
then you're going to make. So here, let's look at.
so you don't know what is the initial value, so essentially you can go forever. So at a certain point you should widen. How you widen it?
So the way we would do it is you would say Fibonacci of some natural number.
Okay, so the natural number is given, or is
Yeah.
it abstraction?
Yeah, it's an abstraction of the input.
Okay.
Okay, so now you run it.
Okay.
Okay, and as your machine is running, it's going to have to allocate stuff. Like every time it makes a recursive call, it's going to allocate something. So you know the recursion bottoms out at some point because you run out of space. Okay, so here's
So essentially you are doing bounded model checking.
in some sense, yeah.
So you are not sound.
No, it's sound. That's the
Okay.
difference.
So at a certain point you should do a widening. What is the widening?
Okay.
You cannot just stop n steps.
Okay, yeah.
Because this will be unsound. So at a certain point you say, okay, because if I go n plus n, you have to over-approximate
Okay.
the behavior. So you should have a widening. I'm trying to see what is the widening.
Okay, so right, so push and bind are going to so we've got this finite heap, and now the other important thing is that the heap. Okay, so let's say you go to write into some location in the heap, and there's already something there. Okay, so what you do is you just join them together. So the heap maps to sets of things, and when you have a conflict, you just join them together, and now you've got a set of things there.
This joint can grow up infinitely. So somehow you have
But the
over-approximated
the set of things you can put in there is finite, so they can't grow. They can't grow forever. I can work out all of the details for you. Okay. But the sort of important point is that when you go to look something up in the heap, there's now a set of values there, and you just non-deterministically choose something. So you go from a deterministic infinite state machine to a bounded non-deterministic machine. Okay, and I'll tell you all about the details. Yeah. So if you wanted to get an interpreter out of it, your push and bind are just going to produce fresh addresses. And if you want an abstract interpreter, like if you want to do something like 0 CFA, then you're just going to choose, so push is going to choose the label of the call site, and bind is going to choose the variable name, and so on. Okay. And then you just iterate these things. Because you know that it's finite, you just iterate them to a fixed point. And you get things like this, all right? And the big insight for me was that we're just talking about interpreters, okay? I mean, they're abstract interpreters, but they're just interpreters. So you can bring the stuff that you know about interpreters to this problem space. So, right, it's just an interpreter, and one of the things, so if the heap is your sort of resource for precision, right, and the way that you get these splits in the graph is that you had two things sitting in the same heap location. So you've got this finite resource, which is the heap, and you lose precision when multiple things reside in the same heap location. But it's just an interpreter. So let's write a garbage collector, all right? And this is the kind of thing that I mean by observing that it's just an interpreter means that you can take stuff that you know about interpreters and bring it here. And this is just one idea. So write a garbage collector. And what happens is that this thing, you get a much tighter characterization of your program here, because you're able to collect space that wasn't reachable. And then when you go to write something and do it later, it's the one thing that's there.
I'm still confused, because I thought the point of keeping multiple things in the heap was not. I mean, it was also for soundness, right?
Yeah.
So if you're just going to blow away stuff that was there previously, you may lose.
Yeah, but it's a sound blowing away, because you run your garbage collector and it says I can't reach this in the future. I mean, it's sound in the same way that garbage collections sound, right? I know that this location isn't reachable, so blow it away. And then later, if I need to write something into that location, that's fine. And there just won't be anything sitting there when you go to write into it.
Okay, I guess I don't have the intuition.
I think it's just an optimization for the analyzer in a way.
Yeah.
Just say while doing the analysis, I'm allocating these cells. Now I know that this goes out of scope.
Yeah.
I
So
still keep
free
it because this is there, but it's unreachable. I know this thing is because maybe something allocated inside the procedure,
Okay.
and then this thing escape. Does not escape, so you can just get rid and actually it's something you do when you do study.
Yeah.
Heap analysis. You get rid of the unreachable nodes to make things smaller.
Mm.
So another.
There was a paper in SES by Anders Meller and his students in SES 2009, maybe. They were using some similar technique for their JavaScript analysis.
Oh, okay.
Just how they do some kind of lazy propagation these things. Anyway.
Okay, I'll have to look at that. So I know this stuff from Matt Might's work on abstract garbage collection. Yeah, another insight is that this thing is just a finite state machine, and you think, okay, so I'm approximating this Turing-complete language with a finite state machine, which is a little bit like bringing a knife to a gunfight. And you could think about richer models here. So one is like, why not use a push-down automata? And that has the nice property that now in your abstract space, you're going to the stacks on your push-down automata match the stacks in your program. So you can do a really precise job of reasoning about the stack here. And you get a I know it's light, but you get a nicer, tighter approximation of the program as well. And then a sort of natural thing that you might want to do is to use both of them. And there's a technical problem that you've got to solve here, because if you've got a push-down automata and you want to crawl the stack to do garbage collection, that's not something you can typically do with a push-down automata.
Sorry, I lost the intuition for this slide. So what's on the top?
The top is just the original finite state approximation. One is using garbage collection.
So now you get rid of
The other is using a push-down approximation. And now we'd like to...
more precise than the other one, isn't it?
They're really kind of incomparable.
Oh, dear.
And then you would
Okay.
like to use both of these techniques. And Matt and I have a nice EFP paper on how to combine these.
So what you prove is that essentially you can get something which is
That's more precise than.
more precise and faster.
Yeah.
Because you have fewer states and you have
Yeah.
push-down.
Yeah, I think we should wrap up.
Okay, so let me wrap up. And there are other things that sort of optimizations that you can start doing once you just start seeing this as a interpreter, like writing a compiler rather than an interpreter, and it improves the performance. So we get better memory. The transitions are faster, and the overall analysis time is dramatically improving here. So this is 2 to 3 orders of magnitude better. Okay, so it really can be automated just by composing with this stuff. All right, so I showed you about our verification environment. I talked briefly about our sort of approach to making these things computable and fast. And there's some papers, this Uppsala paper. This is the paper on combining push-down analysis and garbage collection. And this is the paper about making these things fast. That's just a draft that's on archive these days. So, thanks.
Cool. Thanks a lot.
Yeah.